Hello everyone, I am AK Kulkarni, working as an assistant professor in electrical and electronics. So in second session of the power system analysis, as we are discussing about the module 3 symmetrical components, and further we are going to cover the various topics related to the symmetrical components in this session. So shall we begin? In this session, we are going to start with the new topic, that is expression for phase voltages in terms of symmetrical components. Okay, so in this module, as I discussed in the previous session, so here we are going to convert what the unbalanced phasor values with the help of these symmetrical components. As we know, there are three types of symmetrical components we are going to have. One is a positive sequence component, negative sequence component, and zero sequence component. These are the respective phasor diagrams for each component, so which we already discussed in our previous session. Okay, so with the help of these components, we are going to convert these phasor voltage in terms of what symmetrical components. So we are going to convert in terms of positive sequence, negative sequence, and zero sequence component. Okay, so let us consider the figure number A. So that is a figure number 3.2a. So this figure represents what? It is a phasor diagram for our positive sequence component. So from this figure, so if I consider the phasor VB1, so 1 represents what? One subscript is meant for positive sequence, 2 subscript it is meant for negative sequence, and 0 is meant for zero sequence component. Okay, so according to that, from this figure A, so the phasor VB1 with respect to, what is the relation of a VB1 with respect to VA1? So VB1 is leading with respect to VA1 because we considered which direction? Anti-clockwise direction over here. So if we consider it as it is in anti-clockwise direction, according to that, the phasor VB1 is leading with respect to VA1 by an angle 120 plus 120 is how much? 240 degrees. So VB1 is leading VA1 by an angle 240 degrees. And similarly, the phasor VC1 with the relation with respect to VA1, it will be equal to what? VC1, once again it is leading with respect to VA1 by an angle 120 degree because the direction is in anti-clockwise direction. So according to that, VC1 is leading VA1 by an angle 120 degree. So shall we represent with the equation? No. Okay, so according to that, VB1 is equal to what? VA1. So it is making what is the angle between VB1 and VC1? 240 degrees. So VA1 at an angle 240 degrees. Similarly, VC1 is equal to what? VA1, and the angle between these two phasors is how much? 120 degree. So angle is 120 degree. So shall we represent these two equation in terms of with the help of A operators? Okay, so as we already studied the A operator in our previous session, so where A represents what? So A is equal to, it is equal to what? 1 at an angle 120 degree. So where it is having a magnitude of 1 and angle of 120 degree, and A square is equal to what? 1 at an angle 240 degrees. And similarly we stated various terms with respect to this A operator in our previous session. So we are going to use these notation wherever possible. Okay, so shall we use the A operator wherever necessary? According to that, these two equation further reduces to what? VB1 equal to VA1 and 240 degree. So 240 degree having a magnitude 1 represents what? A square. So instead of writing this angle 240 degree, we are going to write it what? A square having a magnitude 1. So 1 into VA1, we are going to get VA1. And similarly VC1 is equal to what? VA1 at an angle 240 degree. So sorry, 120 degree. So 120 degree represents what? A is equal to having a magnitude 1 and angle 120 degrees. So here that equation further reduces to what? VC1 into A into having a magnitude of what? 1 into VA1. So that is nothing but VA1. So VC1 is equal to what? A into VA1. Now let us consider a negative sequence phasor diagram. So according to our previous session, so the difference between a positive sequence and a negative sequence was its phase sequence. Is it so? So according to that, here the phasors will get interchanged over here, if you observe carefully. Okay, so according to that, now VB2 is leading, once again it is leading with respect to VA2 by 120 degree, but in case of positive sequence it was leading by 240 degrees, but in negative sequence it is going to lead with respect to VA2 by 120 degrees. So for 120 degrees having a magnitude of 1, the notation we are going to use was A. So according to that, VB2 will be equal to what? A into VA2. Similarly, VC2 is leading with respect to VA2 by an angle how much? 240 degrees. So for 240, what is the notation we are going to use? A square. So further it is simplified to what? VC2 is equal to A square into VA2. And similarly for this figure number 3, as we know the magnitude of these all phasors in case of zero sequence component, it will remain same, but there is no phase angle between them. So for that reason, so VA0, all the phasors are equal to each other, so the magnitude of all the phasors will be equal to each other. So VA0 will be equal to VB0, and after obtaining the respective positive, negative and zero sequence component equations, then as we know there are three unbalanced phasors. So this is the unbalanced phasor representation which we taken into our consideration in our previous section. Is it so? So this is what unbalanced phasor. It consists of VA represents VA, VB and VC are the three unbalanced phasors. Okay, so these three unbalanced phasors can be resolved into three sets of balanced phasors. Okay, so these unbalanced phasors can be resolved into what? Three sets of balanced phasors compressing of the phasor A. So the phasor VA will be equal to what? The sum of positive sequence component VA1 and respectively negative sequence component VA2 and zero sequence component VA0, which means, so respectively we are having the three components, right? For positive sequence component, for negative sequence component, as well as for the zero sequence component, we are going to consider the respective phases. Okay, so phase A respective value for the positive sequence component, phase A's respective value for the negative sequence component, and phase A's respective value for our zero sequence component. So that will be equal to what? VA will be equal to the phasor A value of zero sequence component, that is VA0, then VA1, that is the phasor A respective value for the positive sequence component, VA2, that is the phasor A value for what? Negative sequence component. So if we add up phasor A's respective zero, positive and negative sequence component, we are going to get what? Unbalanced phasor A's value. Is it clear? And similarly the phasor B's voltage value will be similar to that of our phasor A values. So phasor B's value will be equal to what? The respective phasor B value for positive, negative and zero sequence component. So if we add up all these together, we are going to get the unbalanced voltage for phasor B, and similarly for unbalanced voltage for phasor C will be equal to Vc0 plus Vc1 plus Vc2. So let us represent with the respective equations. Okay, so now after that, let us use the equations which we derived in the previous slide. Those are 1, 2 and 3 in our these expressions. Okay, so va1, so the respective equation we are going to, so it does not have the va naught will be equal to what, to va1 v2, that was the equation we obtained it previously, right? Now vb will be equal to what, vb0. So vb0 will be equal to what? Okay, so now for voltage for phase B, so as we are representing in terms of what, phase A, so as we derived previously the zero sequence component, that was va0 will be equal to vb0, and which will and also will be equal to what, vc0, that is meant for zero sequence component voltage. Okay, so instead of vb0 we are going to represent in terms of phase A as va0 plus then vb1, from the previous equation what we obtained vb1 as, it is equal to va square in terms of a phase va1. So this was we obtained it in our previous slide, right? So instead of writing vb1 we are going to write it as, excuse me, a square into va1. Okay, so instead of vb1 I'm going to write it over here. And similarly vb2 what we obtained it previously, so vb2 is equal to what, a into va2. So instead of vb2 I'm going to represent it by a into va2. Now similarly for the phase C's voltage value will be equal to what, instead of vc0 we need to represent with what, phase A, right? So for zero sequence component voltage value, that was va0 will be equal to vb0, which will be vc0. So in terms of a phase, so it will be equal to what, va0 obviously. Then vc1 what we obtained previously, vc1 was equal to what, a into va1. So instead of writing vc1 I'm going to represent it a into va1. And vc2 what we obtained previously, vc2 is equal to a square into va2, that was in terms of what, phase A. Okay, so instead of writing vc2 I'm going to write it represent it by a square into va2 over here. So thus we obtained three equations, right? So these three equations we are going to write in the matrix form. Okay, so these are what, the unbalanced voltage, and this entire equation it is represented in the sequence component at one phase. So here the phase we utilize it is the phase A. So after further simplification, so these are the unbalanced voltage VAB, VA, VB, VC, which is equal to, so let us take the all the sequence components voltage aside. We okay, so if we simplify it, so here the magnitude of va1 is what, va0 is how much, 1, and the magnitude of vm is 1, and the magnitude of va2 once again its value is 1. So 1 1 1 I'm going to write over here. Then move to the next equation. What is the magnitude of this va2 or va0 we are having for the second equation? Once again it is having a magnitude of 1, so 1. And then next, what is the magnitude for this value? A square. So let us represent over here a square. Then what is the magnitude of for this value? We are going to get a, so let us represent it by a. Now let us move to the third equation. Okay, for this what is the magnitude we are having? 1, so we are going to represent it by 1. Then similarly what is the magnitude for this va1? That is a you are going to write over here. And similarly you are going to get at a square over here. So what else is remaining over here? All the sequence components voltages respect to what phase A, so that is VA0, VA1, VA2. So if you do the cross multiplication, we are going to retain this original form of the equation, that is 1 into VA0 plus 1 into VA1 plus 1 into VA2. Then second equation was what? VA0, right? So 1 into VA0, second one plus a square into va1, a square into va1. So if you do the cross multiplication, we are going to get this original form of the equation. So this is the matrix form of our equation for what? For unbalanced phasors in terms of symmetrical component. So these are the symmetrical components we are going to use over here. Okay, so next we'll move to the next topic, that is expression for symmetrical component in terms of phase voltage. So the previous topic was what? The expression of phase voltage in terms of symmetrical component. Here it is and vice versa. We are going to express the symmetrical component in terms of the phase voltages. From the previous expression, what we obtained, where we are going to represent the matrix from our previous equation with some notation. So let us represent this entire matrix by what? T. So then according to that, our main equation will be simplified as this much, right? So these are our unbalanced phasor voltage into this matrix T into symmetrical components value. Okay, so now we are obtaining what? Symmetrical component in terms of phase voltages, right? So let me take this symmetrical component to this side and these phase voltages to this side. So according to that, what will happen? So this matrix will be what? It will be inverse of this matrix. So we are moving the matrix from RHS side to the LHS side and LHS side to the RHS side. So according to that, this equation represents what? The value of symmetrical components in terms of phase voltages. As we know, the inverse of any matrix will be equal to what? Adjoint of the matrix divided by the determinant of the matrix T. So here the T matrix we considered as this value, right? Okay, so according to that, for this reason, first we need to find out the determinant of T. Okay, so let us find the determinant of T. So determinant of any matrix will be equal to what? So first row and the first value, first row and first column. So one, if I consider this value, so it will be cross multiplication of this minus the cross multiplication of these two values. So according to that, 1 whole into what? A square into a square minus a into a. So which means so 1 into a to the 4 minus a square. So which I think these, how to get the determinant and the adjoint of the given matrix you already studied in the previous module and also in your mathematics subject. Okay, so no need to explain this particular to find out the determinant of the particular matrix. Hope it can be understood from the uh, given equations. So this is what we are going to get after simplifying the determinant of the given matrix, and we are going to get a, so 3 into a minus a square. So this is the determinant of the matrix T. After that, further we are going to get the adjoint of the T. So you can go through this matrix, it can be easily understandable as you already familiar with how to obtain the adjoint, I think so. So you can get to know from this equation how to obtain the adjoint of T. So no need to explain, I think so. Okay, so now we'll move to next. Okay, so after obtaining the adjoint of the given matrix and the determinant of the matrix, so let us substitute the value of those adjoint and determinant in this equation to get the inverse of matrix T. So after substituting each value, so you are going to get the inverse of the matrix T as 1 by 3 and this matrix. So if you observe carefully, if I compare with the matrix T with the inverse matrix T, so here the values are getting interchanged over here. So this is you can notice over here if I compare with the matrix T. Okay, so after that the inverse of given matrix T will be equal to what? 1 by 3 into this matrix into the phasor value of the voltage. So which means the symmetrical component voltage now we obtain it in terms of the phase voltages. So if you simply multiply each terms, you are going to get the respective value of zero component, positive component and negative components value. So for the zero components value, so 1 by 3 into VA plus VP plus VC. Now multiplies these two matrices respective value of 0, positive and negative component value we are going to get in terms of what? Unbalanced phasor values. Hope this can be understandable for every one of you. So no need to explain how to do the cross matrix multiplications and everything. It is clear for you. Okay, so after obtaining the voltage values, similarly we can obtain the line currents for both in terms of phasor values in terms of symmetrical component and the symmetrical component values in terms of phasor values. So wherever the phasor voltages are there, we are going to replace it by the current. Similarly, the wherever the symmetrical voltage values were there, we are going to represent it by the current value. So it is the same as that of our phasor value. So here only we are going to replace the voltage by current value, respective current value.